saw before in the example that f of x is equal to x squared sine 1 over x, that um, f prime might exist everywhere. Prime x exists for all x, but f prime is not continuous everywhere. So f prime is not continuous, at 0, right? So in particular, derivatives which exist at every point on an interval, um, it does not have to have that the function is continuous. However, under certain conditions, you do have this result. Okay? So theorem 5.12. Suppose f is real differentiable. Suppose f is real differentiable. Function on AB, and suppose f prime of A smaller than lambda, smaller than f prime of B. Okay, then there is a point x in AB. There is a point x in AB. Oops, not closed interval, open interval AB, such that f prime of x is equal to lambda, right? Proof. This does not mean that the function is continuous, but it is taking every single intermediate value, right? So intermediate value theorem says that, oh, if your function is continuous, it takes everything in between. This is saying the other way around. The function takes everything in between. Does not imply it's continuous, but it does still take everything in between. Okay. Similar result holds if f prime of A is greater than lambda greater than f prime of B. The proof follows the same argument. So let g of t is equal to f of t minus lambda times t. Okay. Basically, then I want to show that there is at some point g prime of t is equal to g prime of x is equal to 0. Okay. Well, what happens at A? Then g prime of A is smaller than 0. Why is this true? Well, f prime of A is less than lambda, right? What is g prime of A? It is f prime of A minus lambda, right? The t goes away when you take the derivative. So that g of t1 is smaller than g of A for some t1 belonging to AB, and g prime of B is greater than 0. So there is some t2. So there exists t2 belonging to AB such that g of t2 is smaller than g of B. Did I say things wrong? G of t1 is Right. No, no. Okay. Uh, no, this is fine. Yes, both sides are correct. Okay. So hence, well, you have something that is smaller than A and smaller than B. It is going in a minimum, so there should be some minimum on AB since f is continuous. Hence, G attains its minimum. Attains its minimum on AB. Every function attains its maximum and minimum at some point x such that A is smaller than x smaller than B, right? Then by theorem 5.8, g prime of x is equal to 0. Hence, f prime of x at that point is equal to lambda as we wanted. Right? We are using the fact that f is real differentiable implies that f is continuous, right? So even though f prime is not continuous, f is still continuous. An important consequence of this is corollary. If f is differentiable on A to B, if f differentiable on AB, then f prime cannot have any simple discontinuities. Any simple discontinuities. That is, if both the limits exist, then it is continuous. Okay, you cannot have that, oh, the limit from the left exists, the limit from the right exists, but the limits are not equal. Okay, if the limits exist, they have to be equal, but you could still have a discontinuity of the second kind where the limits don't actually exist. Okay, so note f prime may still have discontinuities of the second kind. Okay. Then let us look at one of the major results that we get that is super useful with derivatives and limits. Like, this is one of the most useful results for calculating limits once you know that both the functions are both the function is differentiable. Okay, so this is called L'Hopital's rule. L'Hopital's rule. L'Hopital's rule. Fun fact: I'm Indian. In India, we were taught this under the name L'Hospital's rule. The guy was French, so it's pronounced in my horrible imitation of how it should be pronounced. It's pronounced L'Hopital's rule. Okay. Since we don't have to tell each other what the rule is, it's you don't have to say it. It's fine, but generally it's pronounced L'Hopital's or something like that. Theorem 5.13. Whenever I use L'Hopital's rule, I will just abbreviate it as LH rule or just write L apostrophe H. Okay. Suppose f and g are real differentiable in AB. Real differentiable in AB. And furthermore, assume that g prime of x is not equal to 0 for every x in AB. Okay. So technically we can take extended reals where minus infinity smaller than or equal to a, strictly smaller than b, smaller than or equal to infinity. So this result holds for extended reals rather than just reals. Furthermore, suppose the limit of f prime x over g prime of x exists and is a. Okay, as x tends to a. Okay, great. Then if f of x goes to 0, g of x goes to 0 as x goes to a, or g of x goes to plus infinity minus infinity. So let me just say plus minus infinity as x goes to a. All of these results hold for b. So I'm just going to write b here. Okay. Let me write it in a different color so that b holds for b. Similarly. Okay. Then the limit of f of x over g of x as x goes to a is also a. Okay, which is, in other words, you are saying that if limit f prime of x over g prime of x exists, then it is under these circumstances, then the limit of fx over g of x exists and is equal to the limit of f prime x over g prime of x. Okay. Proof. So the book has slightly more cases where it shows in things. Okay. I am just going to prove for half of them. I'm not going to go through everything. You can consult the book. We'll show for negative infinity is smaller than or equal to capital A smaller than infinity. Analogous proof. Analogous for A is equal to plus infinity. Okay. So I'm assuming for now that A is finite, or at least there is some rational, real number greater than A. Okay, you can reverse the arrows of the entire proof, and it'll hold for the other way. Okay, choose Q belonging to R such that A is smaller than Q strictly, and R belonging to R such that wait, let me just say Q. Well, whatever. I could have just said all of this in one shot. R Q R such that A is smaller than Q, R smaller than Q. Anyway, in this case, by because limit limit of f prime x over g prime x approaches A, we have that there exists a point, there exists C belonging to AB such that A smaller than x smaller than C implies f prime of x over f prime of A, f prime over g prime of x, not f prime of A. G prime of x is strictly smaller than R. Right? Similarly, you can find something where it is greater than R, but that's if you want to show it for a positive infinity, then you can do the exact argument the other way around, as I was saying. Then, if A smaller than x smaller than y smaller than C, then the previous theorem shows, theorem 5.9 shows there exists T belonging to xy such that f of x minus f of y over g of x minus g of y is equal to f prime of x f prime of t. Over g prime of t smaller than r. Okay. Now, suppose f of x and g of x go to what do you call? Suppose f of x and g of x go to 0. Suppose f of x approaches 0, g of x approaches 0, as x goes to a, then well, what is happening? The left hand side, f of x is going to 0, g of x is going to 0, so I get minus f of y over minus g of y, which is just f of y over g of y smaller than or equal to r. Right, in the limits, you generally have smaller than or equal to, which is strictly still smaller than q. Right. So next, suppose that suppose g of x goes to infinity. I'm going to assume positive infinity. holds for negative infinity very similarly. Then we keep y fixed in the previous one. Can't even draw a star. Then keeping y fixed, we choose a point. We can choose a point C1 belonging to a comma y such that gx is greater than gy, right? Because g of x is going to infinity. And again, because it's going to infinity, I can assume that g of x is greater than 0 if a between x between c1. Okay? Then multiplying by g of x minus g of y, and then dividing by gx, we get, well, if I multiply by gx minus gy and divide by gx, I get f of x minus f of y over g of x, right? So I get f of x minus I'm going to rearrange things. So f of x over g of x is strictly smaller than r minus, well, on the top technically I had f of x minus g of x, right? Oh, sorry, f of x minus f of y. So I get smaller than r minus r times g of y over g of x plus f of y over g of x. Okay? Why? Because I multiplied even the right hand side by g of x minus g of x minus g of y over g of x, which is just 1 minus g of y over g of x. Right? Great. Letting x goes to a, letting x approach a, there exists again c belonging to c2 belonging to a comma c1 now, such that f of x over g of x is smaller than q for every a smaller whenever, so I don't need this, a smaller than x smaller than c2. Okay. Therefore, in either case, I get that for any q, therefore, for any q, such that a smaller than q, I have that there exists c2, such that f of x over g of x is smaller than q if a smaller than x smaller than c2, right? Similarly, for a if negative infinity is smaller than a smaller than or equal to positive infinity, right? We can show and we can show and wait, and p smaller than a. We can show we can find a C3. We can find a C3 such that um p smaller than f of x over g of x, a smaller than x smaller than C3. Okay, and therefore, well, this is true for every p and every q satisfying these conditions. Therefore, limit x approaches a, f of x over g of x is equal to a. Okay. If a was indeed equal to negative infinity, then such a p does not exist. If a was indeed equal to positive infinity, such a q does not exist. Okay. And there you're showing that, oh, this limit is greater than this limit is greater than every single rational, so it has to be infinity, or this is smaller than every single rational, and hence it has to be negative infinity. Okay. So let's compute derivatives of higher order and use that to compute what is called the Taylor's look at what is called the Taylor's theorem. So by the way, this completes the proof. Derivatives of higher order and Taylor's theorem. Okay. Definition. If f has a derivative on the interval a and f is itself differentiable, so if f has derivative f prime on an interval and f prime is itself differentiable, we can we denote the derivative of f prime by f double prime, okay, and call it the second derivative and call it the second derivative. Nearly all of you should have seen this before. Second derivative should not be unfamiliar to you. Notation, nth derivative, notation, nth derivative of f is denoted by f bracket n. Okay, of x. F to the 0 of x, well, 0th derivative of f is just f of x for notation. Okay, and if the nth derivative exists, then that means that f is differentiable in an interval around x. F to the n minus 1 is differentiable in an interval around x. So if nth derivative of f exists at x, i.e. then f to the n minus 1 is differentiable and hence continuous on some interval around x. Okay, so we can assume that whenever the nth derivative exists, I can find some interval where it is continuous and differentiable. Then Taylor's theorem. Suppose f is a real differentiable function. Suppose f is a real function on AB and is a positive integer and belongs to n. F to the n minus 1 is continuous, is differentiable on AB, is differentiable on AB, well, is continuous on AB, closed interval, and Fn of t exists for every t in the open interval AB. Okay, because we have not defined one-sided derivative, the derivatives only exist inside, not inside itself. That alpha and beta be distinct points of AB. That alpha comma beta distinct points of AB and define the polynomial p of t is equal to summation k is equal to 0 to n minus 1 fk of alpha over k factorial times t minus alpha to the k. Okay. Then there exists x between AB such that, sorry, not between AB, between alpha and beta, such that f of beta is equal to p of beta plus f to the n of x over n factorial times beta minus alpha to the n. Okay? Note, for n is equal to 1, this is just a mean value theorem. This is just mean value theorem. Okay? What is this theorem saying? In other words, the theorem says that f can be approximated by a polynomial of degree n minus 1. F can be approximated by a polynomial of degree n minus 1. Okay. Proof. In fact, we can do better. We can bound the error, right? And we can bound error. And we can bound the error. We are bounding the error using the bounds on the nth derivative at x. So if we know the bounds on the nth derivative, we can bound the error in the maximum fashion. Okay. Proof isn't too hard. Let m be such that f of b f of beta is equal to p of beta plus m times beta minus alpha to the n. Okay, and put g of t is equal to f of t minus p of t minus m times t minus alpha to the n. Okay, so basically I am looking at a function g of t. I want to find when it's 0, right? When it's 0, that would be exactly saying f of beta, this function I know is 0 at beta. Okay, I want to show, we want to show that n factorial times m is equal to f to the n. So nth derivative of f for some x for some x belonging to alpha comma beta. Right? Now, since I defined g of t this way by star g to the nth derivative of t is equal to, since I know that the nth that f of t is differentiable, polynomials are differentiable, I know that the entire function is differentiable, so I get f to n of t minus, well, p of t is actually only n minus 1 degree polynomial, right? It's a sum of degree n minus 1 terms, and so its nth derivative is 0, so minus 0 minus m times n factorial. Okay, because in the last term I'm going to get n times n minus 1 times n minus 2 all the way into derivative of t minus alpha, which is just 1. Okay, therefore enough to show gn of t is equal to 0 for some x, not gn of t. Gn of x is equal to 0 for some x. Okay. Now, what do we know? Since p to the k of alpha is equal to f to the k of alpha, we have g of alpha is equal to g prime of alpha is equal to G double prime of alpha is equal to dot 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 is equal to G to the n minus 1 of alpha is equal to 0. Okay? So G of alpha is equal to 0, G of beta is equal to 0. So G prime of x, therefore G of alpha comma G of beta is equal to 0 implies there exists x1 between alpha comma beta such that G prime of x1 is equal to 0. Right? Therefore, G of alpha comma G prime of alpha comma G prime of x1 is equal to 0 implies there exists x2 belonging to alpha comma x1 such that G prime of x2 is equal to 0. Going on, I get therefore there exists G prime G not prime G n minus 1 of alpha G n minus 1 of x n minus 1 is equal to 0 implies there exists xn belonging to alpha comma xn minus 1 such that G prime of xn is equal to 0. Oops, let me write it properly. Such that G prime of xn is equal to 0 as required. As required. Okay, that completes the proof. If you're not 100% sure why this is equal to 0, this is simply because if you look back at here, right? P to the k of alpha is f to the k of alpha, and the n minus everything until the nth derivative has a t minus alpha term. So this is going to be 0 at t minus alpha, right? So 0 at t is equal to alpha till g to the n of t. Okay, so from 1 to n minus 1, we have that this is 0, these are equal, and hence the entire term becomes 0 at alpha. Okay. Feeling so tired. And now we can start. You have seen all of these things before. You have seen most of these things before. Maybe not at this exact result, but you have seen how to take derivatives of real functions when the functions are going from reals to reals and everything. You have seen all of this before. What you might not have seen is what to do when your function is vector valued, right? Depending on how much calculus you have taken, you can only you can look at it for. You might have seen derivatives of vector valued functions, gradients and other things, but otherwise you might not have seen it. Okay, so remark, the original definition that we defined that is f of x minus t minus f of x or t minus x, that has nothing to do with reals. Remark. So let me just differentiation of vector value functions. Definition of derivative can be generalized without any change. Can be applies without any change. Does applies without any change. Without any change to complex functions. Complex functions defined on A to B. Defined on A to B. And the theorems 5.2 and 5.3, which talk about, if the function is differentiable, then it is continuous, and if the function is differentiable, then the sum of the functions is differentiable. Both also work for for complex numbers. So theorems 5.2 as well as 5.3. 5.3 with their proofs remain valid. Right? Now, if it's a complex function, you can split it up into two parts. Let f1 and f2 be the real and imaginary parts. Real and imaginary parts of f, i.e. f of t is equal to f1 of t plus I times f2 of t. Okay, then both a and b are f1 and f2 are real with both f1 comma t, f2 comma t real functions. Okay, maybe not with both, then both are real functions. And clearly f prime of t is equal to f1 prime of x, not from prime. Since I've been following the notation of the book, the derivatives are all at a point x, and t is the variable point which moves closer and closer to x. So f1 prime of x plus I f2 prime of x. Okay? Therefore, f is differentiable at x if and only if both f1 and f2 are differentiable at x. At x. Okay? Um, this does not. This is not just true for reals. Sorry, for complex. We can also apply um, the definition. We can also generalize. Also generalize the definition to vector valued functions, to functions f bar, which map ab to rk, okay, to define f prime of x. You have to be slightly careful. The distance now will have to be in terms of norm, okay, and phi t is now for each for a point in rk. Phi of t is then defined then for a point, then then a point in rk, and the distance is taken with respect to the norm. Okay. In other words, f prime x, i.e., f prime x is a point, is the point of rk if there is one, for which limit t approaches x f of t minus f of x over t minus x minus f prime of x is equal to 0. Okay? And oops. And f prime of x is a function with values in rk. Is a function with values in rk. Okay? Once again, if f prime of x is equal to if f of x is equal to first if f of t is equal to f1 of t dot 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 fk of t, then f prime of x is equal to f1 prime x fk prime of x, and therefore and hence f prime f bar is differentiable at x, is differentiable at x if and only if all of f1 to fk are differentiable at x. Okay? We'll look at some results related to this, but for now I'm going to stop here. Okay? Actually, this is nearly the end of the chapter. Oh, okay. I'll just stop here. In either way, I'll finish off the chapter tomorrow.